Hello guys, I am Saurabh Gupta and I am a student of IIT Bombay, currently studying mechanical engineering, and I have cleared the IIT JEE in the year 2010 and secured an EIR of 443. I have also cleared the second stage of National Chemistry Olympiad, which is conducted by HBCSE, and today I am here to discuss something about alkyl halides and aryl halides. Now this is also another class of organic compounds, the study of which we have started with alkanes, then we have studied alkenes and alkynes, and today we are going to study the properties of alkyl halides and aryl halides. First of all, what is the alkyl halide? Alkyl halide is simple organic compound with a halogen derivative. That is, there is some substituent of either fluorine, chlorine, bromine or iodine. For example, let us take any simple alkane, a simple open chain compound, and this is an alkyl halide because there is a halogen substitution in the parent carbon chain. Now this X can be F, Cl, bromine and iodine. We have already seen the nomenclature of alkyl halides. We name it as fluoro and whatever the parent carbon chain name is. In this case it is butane, and numbering is very important, so we name it as 2-fluorobutane, 2-chloroputane, 2-bromobutane and similarly 2-iodobutane. Aryl halides are the aromatic halides. Now remember, aromatic halides are not same as the phenyl halides, which is something like, let me tell you after this. Now this halide atom should be directly attached to the benzene ring. It should not be like this X and here there is a benzene ring, or here there is an X. Aryl halides are those halides in which the halogen atom is directly attached to the benzene ring. So this is very important. You should not take this as aryl halide, or this compound as aryl halide, or this compound as aryl halide, because the aryl halide properties are completely different. This is an alkyl halide directly. Okay, there are some differences. There will be some enhancement of properties in these cases, but this will follow the reactions of alkyl halides and not aryl halides. That is why it is very, very important, so that you distinguish between alkyl halides and aryl halides very, very clearly. So now let us begin with the discussion. So organic compounds and these organic functional groups, this is a functional group, but in nomenclature it is always as a substituent. So that is an important point to remember the nomenclature. So now what we are discussing about, the study of organic groups starts with the physical properties, the preparation and the chemical properties. So these three are the major subtopics of each and every organic group, and we have been following the same order for the past few lectures. In this lecture also we will be studying what is the physical properties of aryl halides, and for determining physical properties we will see first what is the structure of alkyl halides and even aryl halides. So the structure defines the physical properties, and it can also define the chemical properties, and the chemical properties tell us how we can prepare the compound. So that means all these things are interrelated. And what is the link? The link is the structure. So let us see what is the proper structure of this alkyl halides. Now, as I already gave you an example, alkyl halides is a compound in which the halogen atom is attached either to an sp3 atom or an sp2 atom. And now this sp2 atom can be, we can call it aryl halides, or you can even say this type of compounds. This is also an example of, this is not either alkyl halides, this is not even aryl halides, but this is called vinylic halides. So this is a special class of halides which is called the vinylic halides. Now this has also got its special properties, but these properties matches with the properties of aryl halides. Why? Because the halogen here is linked to a sp2 carbon, and even in aryl halides you know that this benzene ring carbon is sp2 and the halogen is directly linked to the sp2 carbon. So that means the properties are based on the carbon atom to which the halide is attached, and that defines the physical and as well as the chemical properties. So if you see alkyl halides, the halogen is directly attached to the sp3 carbon, and sp3 carbon has got a tetrahedral structure. As we all know, this has got a tetrahedral structure, And moreover, the most important part of this structure is that this bond, I will show that bond in some different color, that bond has got some polarity. Why? Because carbon and halogen have got definitely different amount of electronegativities. Carbon is lesser electronegative than any of the 4 halogens, and it is the fluorine which is the most electronegative element, hence the polarity of the CF bond will be maximum. So that means if you compare the delta positive and the delta negative charges, then for fluorine this delta negative would be the maximum, and hence it will give you the maximum dipole moment. So here immediately we can derive one physical property, that is the dipole moment. Now from dipole moment, that is dipole moment is highest for the fluorides. Now from dipole moments, what physical properties you can identify? Boiling point, definitely. Solubility in polar solvents also you can determine. So that means the fluorides must be having higher boiling points and more solubility in the water. So you see how from a simple structure we can identify 2 trends in the physical properties, that is for the boiling point and for the solubility, and solubility in polar solvents. That is also very important because all these alkyl halides are polar, so they are somewhat soluble in polar solvents as compared to the corresponding alkanes or the alkenes. Now, but still that solubility is not enough. Why? Because it cannot form hydrogen bonds. This, although the halogen is electronegative, that is this is a polar bond, sorry, the dipole moment has to be opposite, it is towards the negative end of the dipole. So although this bond is polar, but it is not polar enough to be soluble in the polar solvents like water, because it cannot form hydrogen bonds, and if cannot form hydrogen bonds, so it is not sufficient to break the hydrogen bonds of water. So that means how can it go into the water structure? We know all these H2O molecules will be having the hydrogen bonding between each other, and for the alkyl halide to dissolve we need to break these bonds, but unfortunately these halides cannot form hydrogen bonding, and hence it cannot break the bonds between the water. So hence it is not very much soluble, but slightly more soluble than the alkanes and the alkenes. Fine. Now what about the other physical properties? The other physical properties can be like melting point. Melting point is very simple. Now melting point also depends on the symmetry of the halide. Now all the halides are tetrahedral in nature, so that factor actually cancels out. In case of alkenes it was somewhat different. Cis and trans had got different symmetries, but in case of halides all are having the same symmetry, so that factor actually cancels out and we get the same order as the boiling point. Now boiling point, what is the order? What defines the boiling point? Boiling point is defined by the amount of interaction forces between 2 different and similar molecules. That is, if you have one molecule like this, another molecule like this, the amount of interaction between these 2 molecules will determine how much higher or how much lower will be the boiling point of the substance. So now, since these alkyl halides are polar enough, so the interactions would be quite higher as compared to the alkenes and the alkenes. Alkenes, the interactions won't be that high because they are only slightly polar, not polar enough so that the boiling points are higher than the corresponding halides. So this was the boiling point. Now what about boiling point between the isomeric halides? We know that we can also have halides like this, or we can have halides like this, something like this. What about the boiling points of these 2? Now this point we have already seen in alkenes, that boiling point depends on van der Waals forces, and van der Waals forces depend on molecular weight, which indirectly and not specifically molecular weight, they actually depend on the molecular size or molecular area, that is how much area of the molecule is exposed. And here you can see that this is a linear straight chain, so this has got more surface area as compared to this compound, which tends to attain a kind of circular shape, and we know that the surface area of this would be lesser as compared to this. So now the boiling point of this would be higher as compared to this. Although they are isomeric halides, that means the dipole moment and everything would be same, so the polarities are same, so the van der Waals interactions regarding the dipole, that is same, but the van der Waals interactions also depend on the molecular surface area. So that creates some difference in the boiling points. Now, so that was about boiling point, solubility and melting point. What about density? Density of alkenes and alkanes, we have seen that they are lesser than water. So they are less dense than water. What about alkyl halides? Alkyl halides, fluorides are not denser than water, but bromides and iodides are definitely more denser than water, because these two are quite heavy atoms. You know, iodine is so much heavy and bromine is also quite heavy. So that is why the density has increased, but not the chlorides and fluorides. They are quite light atoms. Now, so that was about the density. So we are done with actually the physical properties of alkyl halides. We were discussing about the structure and we got some particular feature about the structure, and we discussed all these 4 physical properties. So that's how the discussion goes on. We catch one particular and one typical property of the alkyl halide or any organic compound which defines most of the reactions and most of the properties. In alkenes, that was the double bond. Double bond defines almost all the reactions of the alkenes, if you remember. Now, moving on to the preparation. Aryl halides and vinylic halides we will discuss after discussing the alkyl halides part, because alkyl halides, there are some important stuff which we need to discuss first. So now, moving on to the chemical properties, what do you think would be the preparation method for the halides? Now, before starting the preparation methods, let us recall 2 reactions which we have already studied. One is halogenation of alkanes. We have seen in the alkanes chapter, the most important chemical property of alkanes is the halogenation, and halogenation produces alkyl or allyl halides. That means that we can actually produce alkyl halides through halogenation of alkanes. So you see, from a chemical property of one substance, we can determine a preparation method, or in fact a laboratory preparation method for another substance. That process, the chlorination process through free radicals, might not be very economical and hence it cannot be used as an industrial method, but definitely it can be used as a laboratory method, because we need only small amounts of the product. Now, what about alkenes? In alkenes also, we have seen that alkyl halides are obtained from the addition of halogens or the hydrohalogenation compounds. For example, HX, which can be HBr, HI, we know that, and X2. So the addition of these 2 compounds or alkenes also give us alkyl halides. So what I want to show here is there is kind of link between all the compounds. From this compound we can derive this compound, and this reaction becomes the chemical property of A and kind of preparation method for B, although might not be economical, but definitely a property or definitely a preparation method for B. So, and this way almost all the compounds, all the category of compounds, alkanes, alkenes, alkynes, alkyl halides, alcohols, aldehydes, ketones, everything is linked to each other. You can prepare one compound from another and you can react one compound to get another. So let us start with the preparation methods. The first one is, I will start with a different preparation method other than those 2. So from alcohols. Now this we haven't studied anything about this because we haven't studied the chemical properties of alcohols. If we study the chemical properties of alcohols, these reactions will automatically come in that. So first we get it from the reaction of ZnCl2, or to be more general, ZnX2. So the reaction of this with an alkyl alcohol, that is, it should not be an aromatic compound, it should be a normal alcohol, normal alkane plus alcohol. Now this gives us what? Obviously it gives us Rx, and this is quite an important method for preparation because it does not give us rearrangement if it goes by the SN2 method. Now what is this SN2 method? We will be discussing in the chemical properties of alkyl halides. So if you don't want to prepare a rearranged alcohol, a rearranged halide, rearranged halide, then we go for this type of reactions. But still, the probability that this reaction will undergo SN2 is quite less. So what we were discussing is the significance of this reaction. This reaction can take the SN1 pathway, which involves the formation of a carbocation, and wherever there is a formation of carbocation, we have rearrangement there. We have rearrangement, and if we have rearrangement, then we have a change in structure, and that is most of the times not beneficial to us, because if we want to prepare a particular alcohol or we want to prepare a particular halide, then we need to choose an alcohol which can give that halide, and most probably we will choose an alcohol with the same structure as that of the halide, because we cannot think in the backward direction. Suppose you are given alcohol and this reagent, probably you can write the mechanism in the forward direction, but if you are asked, you have to prepare this from an alcohol, and then most of the times you will take this R group as same without any change in the structure, but it might not give you the same halide if you take this alcohol because of the possibility of rearrangement. Now we have discussed the mechanism, that is SN1, it goes through a rearrangement method, and mostly this rearrangement is for secondary and tertiary halides. For primary straight chain compounds, you do not get a rearranged compound, you just get a same compound, same halide. That is, this R group does not rearrange and it gives you the same R group plus X. Fine. This was a simple method for preparation of alkyl halides from alcohols. Now in all we have 3 methods totally for the preparation of alcohols. This was one of them. Second method, if you take ROH plus SOCl2. Now tell me, what is this SOCl2? We have seen this before. This is a thionyl chloride. You must have seen this in chemical bonding. Now this is thionyl chloride. Thionyl chloride. Products of the reaction, definitely one product must be RCl. Why? Because we are discussing it under the preparation of alkyl halides. So whatever the product, whatever the reagent is, don't bother. One product must be at least the alkyl halide, otherwise this is a useless reaction. Now, what is the other product? If you see carefully, you can also write the other product. Now, this reaction is again very significant. Why? It is not because we do not get a rearranged product, it is because this SO2 is a gas. So what? Be it a gas, what is the advantage that we get over here? The advantage that we get is the purification of this RCl becomes very, very easy, because you know that organic reactions, there can be multiple products. You can have infinitely many products, and from all those products you will have a major product, and that you need to separate out using the separation techniques. There are various separation techniques. One of them you can say fractional distillation or just simply filtration. Now that is a very, very basic technique. There are far more advanced techniques than that for the purification of compounds. But if you don't have to purify this compound, then it saves a lot of money and it saves a lot of time also. So this is a very good method, because here you directly get the alkyl halides, okay, probably some impurities, but those impurities can be removed very easily. But this major product, the other major product other than the RCl, is removed automatically from the mixture. You take a beaker, add ROH, add SOCl2. SO2 directly escapes out, and what you get is RCl plus some little impurities. In the previous reaction, Rx will be produced, that is from ZnCl2, and there will be a zinc salt also. So you have to purify, you have to separate the chloride from the zinc salt. Now that takes some techniques, but that can also be purified easily, because RCl is not so soluble in polar solvents as we know, but zinc salts are soluble. So okay, in that it is not such a pain, but in some cases it becomes a huge pain to separate out the major product. So it is better that we choose a reaction or we choose a preparation method in which we can get the product in major amount as well as we can purify it easily. So that is why all the chemical properties of a particular compound cannot be taken as a preparation method for some other, for the product of the reaction. We have to see all these factors also. So this was a simple reaction with hyaluronal chloride, and again over here you have got rearrangements, that is secondary and tertiary halides gives you rearranged products. So if you want a particular halide, again this is not a very good method, but the previous one sometimes it can give you a non-rearranged product. But if you want simple open chain primary halide, then almost all the methods are very good. Why? Because primary carbocations if you are getting, then it won't rearrange. Because suppose you want this type of halide, then what will happen is you will have a carbocation somewhere inside the chain, and that would be a secondary carbocation or a tertiary carbocation, and the tertiary carbocation won't rearrange. So hence you will get the R structure retained as such. There won't be any structural change in the R structure, and the structural change comes due to what? We have already discussed this, that the shifting of or the rearrangement of carbocation takes place through either methyl shifts or hydride shifts. So these two are the structural changes that can occur, that a methyl group can be shifting from one carbon to another, or otherwise a hydrogen can shift from one carbon to another in order to get a more stable carbocation. So primary halides, especially open chain primary halides, do not give you a rearranged product, they give you the same R group which is present over here. Fine. This was the preparation from SOCl2. Another preparation can be from PCl5 and PCl3. Again, these two, PCl5 phosphorus pentachloride and PCSC phosphorus trichloride, are two inorganic compounds, and they react with ROH to give us alkyl halides. Now again, this is not a good method if you want a particular halide from a particular alcohol. It can also undergo rearrangements, and this also gives isomeric halides, and this too gives so many alkyl halides. But again, if you want a primary halide, then you can go for both, there is no problem at all. So this was the preparation of halides from alcohols. Now the next preparation method is from alkanes, that we have already seen, that is halogenation of alkanes. I won't discuss it again. If you want, you can just pause the lecture and you can just see the topic on alkanes or the chemical properties of alkanes, or better than that, just refer some NCERT or any standard textbook. So halogenation of alkanes, we have addition reaction of HX and X2 on alkenes. Then we have also seen one more reaction, which is the displacement reaction. Now although we haven't used this word displacement, but we have seen it. Consider this reaction, RCl plus NaI gives you Ri plus NaCl. Now tell me where we have studied this reaction. You can easily tell if you observe the product. This is a halogenated alkane, and that means we have studied this in the chemical properties of alkanes. We saw that the iodination is a reversible process, so we cannot produce it through normal iodination. We need some other method so that this can get in, we can produce this in major quantities, and we saw this method, and we also saw the importance of this solvent acetone. Fine. So this was the displacement reaction, and so these are some reactions for preparation of alkyl halides. Now one final preparation method, let us discuss. These three we have already seen, and there should be no confusion about these. Now as a final preparation method of alkyl halides, let us see this. This is called Hunsdiker reaction, Hunsdiker or Borodin reaction. Now what is this reaction? From the name you cannot just get any clue, but if you see the reaction, probably you get some clue. We will take the silver salts of carboxylic acids, treat them with Br2, and finally what we get is RBr. We should get, because preparation method for alkyl halides, so definitely if we don't get RBr, there is no point in the reaction. So RBr, and we also get AgBr, which is a precipitate, AgBr. Now again, why is this reaction so important? Tell me. I have already explained you by seeing the signs from the reactants. Tell me, why is this reaction important, or what is the advantage of this reaction over the others? Here also the products AgBr and CO2. AgBr is a precipitate and CO2 is a gas. So if you take these two reactants, that is Br2 and this silver salt of carboxylic acid, then you will get RBr over here, and this AgBr will precipitate out and CO2 will go out of the reaction mixture. So the purification of this alkyl halides again become very easy, and hence it is a very good preparation method. Now here also rearrangements are possible, and this is a specific method for bromination or bromoalkanes. We do not use it for either fluoro or iodo compounds because they don't give us very good yields. But for bromo compounds, this is a very important reaction. Now the reactivity of the alkyl group is following this order. That is, if you want a primary halide, this is a very good reaction. If you want a secondary halide, this is not such a good reaction. And if you want a tertiary halide, this is a worst reaction. So tertiary halide, please don't go for this kind of reaction. For primary halide and for bromo primary halide, or for bromo primary alkanes, this is the best reaction because it is designed specifically for bromo compounds. So we are done with these, and as a final reaction, we will see a very familiar reaction, but the products are quite different. That is, if I tell you, if I give you this product, if I give you this reactants plus Br2 gives you what? Now this reaction we have already seen in alkenes, that this will give us what? Yes, this will give us the dibromo halogen. But if I add some substance over here which is called NBS, and the full form of NBS is N-bromosuccinimide. Now this N-bromosuccinimide, what does it do? How does it change the course of the reaction? It actually devastatingly changes the course of the reaction by producing this kind of product. So we see, if we take HBr suppose instead of Br2, then what we get is a halide in the 1,2 position. So you can see that this is in beta position to the double bond and not at the double bond. That is not across the double bond, but it is somewhere in the beta position to the double bond. So you see, just by adding this simple substance NBS, if you want the structure, that is also quite simple, N-bromosuccinimide. From the name you can actually derive the structure. Succinimide is actually a imide of succinic acid. Succinic acid is C, that is 4 carbons, double bond O, nitrogen, and 1 hydrogen. That is succinimide. What about N-bromosuccinimide? N-bromosuccinimide is this kind of structure. So if you add this substance to this reaction mixture, you get a completely different product. Why? Why? Because here in HBr case, we know this is an addition product, and we know that this follows through the SN1 mechanism. It doesn't follow through the it follows through the carbocation intermediate. So again, the reaction will be only one species. The order of the reaction will depend on the concentration of one species. But what if I lower the concentration of bromine? if I lower the concentration of bromine, then what happens is, instead of attacking this double bond, it attacks this carbon instead. So this NBS, just what it does, it lowers the concentration of bromine in the reaction mixture, and the whole course of the reaction changes. You will have different energy diagrams, you have definitely a different product, and you see how much changes can happen if you just add one reagent. So definitely this is a preparation method for a alkyl halide. Now this is not a vinylic halide also, because it is attached to a sp3 carbon, the bromine atom. So you see, you should not get confused between vinylic, aryl and alkyl halides. They are totally separate compounds, and they have got different chemical properties. So let us now move on to the chemical properties. We have discussed the physical properties, we have also discussed the preparation methods. Preparation methods for alkyl halides are quite simple as compared to the alkenes, because alkenes we saw a full elimination reaction mechanism for the preparation method. So that those preparation methods are quite elaborate, but these were quite simple. So let us now move on to the chemical properties. Now in the chemical properties of alkyl halides, this is a very important section. Why? Because there are various chemical properties, and specifically there are two reactions of these alkyl halides which are actually competing with each other. The two reactions are elimination reactions and substitution reactions. Now I mentioned something about the substitution reactions in the first preparation method of alkyl halide, SN1 and SN2, when we were seeing ROH plus ZnCl2. SN1, SN2. These are quite similar to the E1 and E2 reactions which we have already studied. SN1 is unimolecular substitution, SN2 is bimolecular substitution. So these two reactions are actually competing reactions with each other. Why? Because they have same reactants, same reagents, but the difference is the reaction conditions are different. Reaction conditions. That is, if you change the reaction conditions slightly, the major product might be elimination product, or it can go towards the substitution product. For example, if you take ROH, or to be more specific, let us take a particular alcohol, COH, this C. Now if you add a base over here, what does this suggest? Now this suggests that here what am I adding? Not a base OH minus, you add a acid which is HBr. If you take this reaction, what do you think is a major product based on the reaction which we have already studied? That is, we have studied the elimination reactions. So according to you, what should be the product for this reaction? Now to write the product, we know this is an alcohol and this is an acid. So we can go for the dehydration or the acidic dehydration of alcohols. That is, the H plus over here comes and attacks over this oxygen. Now this leaves, forms a carbocation. The carbocation is very stable, and you get a bromination product like this. But what if I change this carbocation so that this has to rearrange? That is, I will add the alcohol over here. I will keep the methyl group here and I will add the alcohol over here. Now, what do you think is the product for this reaction? Now, the product for this reaction would be a rearranged product, and what you will get is HBr and wait. What has happened is I have actually written the substitution product where I forgot to write the elimination product. Let us go back to the previous example. This thing, then we have this thing and this carbocation. Now we have this carbocation, and the first step of the reaction is over. Now the next step is the Br minus abstracts a hydrogen from either of these 9 hydrogens and you get an alkene. Now, this is one of the possible products. But what if I say that the product which I have written earlier by mistake, this one, this is also a very much possible product, and this is also a very much possible product depending on the reaction conditions. That is, if you have more concentration of Br minus or HBr, then you will get this type of product, and you have lesser concentration of HBr and you give it some heat, then you will get this type of product. So you see, just by changing the reaction conditions slightly, I can vary the products, and you see the reactant and the product and the reagent are exactly the same. So that is why what I say is, and this is elimination, this is substitution product, this is elimination product. So that is why I say that elimination and substitutions are two competing reactions. That is, they compete with each other to get their substitution product or the elimination product. So now let us go in the detail of these mechanisms. As we have seen the elimination mechanism in details, we will also see the substitution reactions in details, so that we can compare the substitution and the elimination reactions. For comparing them, we need to have the knowledge of the intermediates, the reaction conditions which will give these products, so that we can easily compare them. Otherwise, there is no logical comparison possible. So, coming to the chemical properties of alkyl halides, chemical properties. First, substitution reactions. As already mentioned, there is SN1 reaction and there is SN2 mechanism. So, reaction is the same, but there are two pathways. And we know that if there are two pathways, there will be different energy diagrams, there will be different products. It might be rearranged in some cases, it might be some other stereochemical change can come in some other process. So, all those aspects we have to cover in these. Now, as an example, as a general idea, let us see what is SN1 reaction. This is a unimolecular substitution. That means the rate of the reaction or the slowest step of the reaction involves a single molecule, the formation of a single molecule. It doesn't involve two molecules simultaneously. So, the rate of the reaction depends on a single molecule. If we consider OH, same HBr, and the first step of the reaction in case of SN1 is very much similar to the even reactions. That is, what we have is the protonation of this group. Now, this case in substitution reactions, we call these as the leaving groups, leaving group, and these as the nucleophiles. We have already seen what is the definition of these terms. Leaving group is a group which leaves from the molecule, and nucleophile is a substance which seeks a nucleus or a nucleus loving substance. It needs to get some positive charge. It is highly attracted towards it. So, when the carbocation is formed, when this group leaves, and when there is a formation of carbocation, this Br minus rushes immediately towards this carbocation and donates its electron density and forms the alkyl halide in this manner. Now, there are certain features about this reaction. That is, this was a planar carbocation. So now you can have attack from top or from bottom. That means, and the probability of the attack is 50-50%, and hence you should get a racemic mixture. But unfortunately, it is very rarely observed that you get a racemic mixture. You will almost never get racemic mixture, because the problem is, along with HBr, you will have the solvent. For example, H2O, and we know that H2O is also a nucleophile. So if there is a carbon center which is deficient in electrons, then H2O or HBr both can donate the electron. and hence the racemic mixture is destroyed, and you can also get this kind of products. We can get back this product, and we can get the enantiomer of this. Suppose there is some C2H5 like this, and this carbon becomes then chiral. So this is a very important stereochemical aspect, that you do not get racemic mixture always in case of the SN1 reactions. And we can also draw the energy diagram for SN1 reactions. Energy diagram for SN1 reactions can be very simply drawn, because we know what are the different steps involved in the reaction. So we will start with, okay, we will name it. We will call this axis as reaction coordinate, and this is the potential energy. Reaction coordinate is the formation of different molecules as the reaction proceeds. So we have the reaction, there is a barrier, there is another barrier, and finally there is a product. Now why do we have two barriers like this? That is because we have got this, sorry, not this, this intermediate formation, and in this case the intermediate is a carbocation. So this minima represents the carbocation, and this is the transition state 1, this is the transition state 2. Again, the stability of the transition states, that is the stability of the carbocation, will define the course of the reaction or the rate of the reaction. If suppose there is some lower pathway available which is lower in energy, then the reaction will proceed in that pathway, and the lower pathway can be if the carbocation can rearrange to give us a more stable carbocation, and that involves also the ring expansion cases. So for an example, let us consider the same question which we have done in case of alkenes. We have this kind of reactant, and we involve same HBr, but in this case we will consider the SN1 reaction in case of instead of the E1 mechanism. So why we are considering SN1 and why we are not considering E1, that depends on the reaction conditions. I showed you that even though you have the same set of reactants and reagents, you can have different products by controlling the reaction conditions. And suppose I consider that, then our final product will look like CH3, and there will be a Br over here. Now again you can see that this carbon is chiral, but still we won't get a racemic mixture, because of the same reason that a solvent molecule can also attack over here, and you can, other than water, you can choose any other solvent molecule which is polar, and that can also form a reaction or a product with this. So that destroy the racemic mixture, and we can have enantiomeric access of one enantiomer over the other. Fine. So this was the reaction coordinates for this reaction, and just to mention, this transition state 2 represents the attack of bromine over the carbocation. So even though it is stabilizing the carbocation, it also has to pass through an energy barrier, because each and every step has got an initiation energy, and without passing through that initiation energy you cannot proceed the reaction in the forward direction. So this was the SN1 mechanism which we have just like that discussed without any problem. So when you discuss like this, even these complicated mechanisms of SN1, SN2, you will feel no problem in understanding them. We will relate the logics of this reaction with the elimination reactions, and we will see the similarities, and so that there is no problem at all. It is as if we are not even learning a new reaction. We are seeing the old one but with slight changes. The change over here is the attack of Br. Instead of abstracting a hydrogen, it is now directly attacking the electrophile, which is the carbocation in this case. Fine, let us move on. Let us move on to the SN2 mechanism. So the SN2 mechanism is a very interesting one, although a bit complicated, but it is seriously very much interesting. It has also got a specific stereochemistry involved with it. If you remember, in E2 elimination case, we also had the particular stereochemistry of the reactant, that is the hydro group and the halogenation group, the hydrogen and the halogen atom both should be anti and planar to each other, that is they should be having an angle of 180 degrees. Then only the elimination reaction is possible. If they have got any other reaction, if they have got any other angle, then the compound must go towards that conformer in which this reaction is feasible, in this angle is feasible, and let it be a less stable conformer, it doesn't matter. If we want an elimination product, we need to go to that conformer. Fine. This reaction also has particular stereochemistry. Let us see how. This is the reaction coordinate. As the different reaction and the species produced, we will be drawing it. Let us consider SN2. No SN1. SN1 we are finished. SN2. OH and okay, here let me draw the same molecule but in a different form so that we can understand it better. Let us take this carbon which was tetrahedral, the groups in this way, OH, CH3, hydrogen, CH3. It is the same molecule which I have already drawn, but with slight change. That is, we now want the carbon, the tetrahedral carbon, to be our focus. We don't want the overall molecule. These groups are actually not so important. So now we will take our, suppose, Br minus. Instead of Br minus, let us take some other nucleophile. Let us take, suppose, HCN, or let us take our nucleophile as the Cn minus. Now SN2 reaction is what? A reaction which is bimolecular in nature. That means the order of the reaction depends on the concentration of two species. Obviously the two species are the alcohol or the reactant and the, why are we considering alcohol? We are supposed to consider alkyl halide. Now the alkyl halide and obviously the nucleophile. Fine. So now what should happen over here? What happens is that this Cn minus approaches this carbon in such a way that it avoids repulsion from all these groups. So it approaches in a direction where the repulsion is minimum. That is, it approaches in somewhere this direction. Now if it approaches from the opposite direction, then what happens is it faces a lot of repulsion from the alkyl halide, and hence it approaches from the back direction. It is almost opposite to the direction of the alkyl or the halogen atom. Now let me remove this arrow. This arrow is not important. So it has approached. Then what happens? Then a very important intermediate forms. The energy diagram of this reaction is just this much. That is, there is only one maxima. That means there is only one transition state and there is no intermediate production. And if there is no intermediate production, the transition state has to be really special. Then the transition state, okay, I will draw the transition state separately. Hydrogen CH3. Now this gives us a transition state in which this CH3, hydrogen and this CH3, you can draw the hydrogen in such a way that this somewhat comes this way, and this X, this Cn minus, delta negative, delta positive and delta negative. So this is actually our transition state. Now you see that the carbon has got 1, 2, 3, 4, 5 bonds. That is, we have a pentavalent carbon transition state, which has to be very much unstable because the carbon cannot expand its octet and because of the lack of d orbitals. So this bond is forming and this bond is going to break. And you see the partial charge densities. We know that carbon halide bond has got a dipole moment. That is, this is the positive center and this is the negative center. So that is why without even the formation of a carbocation, it involves the reaction, it attracts the nucleophile towards it because of the polarity between the carbon and halogen. In case of the SN1 reaction, we had got a proper carbocation and hence we know that nucleophile is attacked. But in this case, what is the reason that the nucleophile is attacking? The reason is because of the polarity of the CX bond. Fine. So if this is our transition state, how is this possible that this transition state exists? I mean, what is the geometry of the transition state? If it is pentavalent, the geometry is that this C and this Z and this hydrogen, that this the three groups are in a plane. So there is a plane which contains these three groups. Now, what about the Cn minus and the X delta minus? That is exactly in the opposite line to each other, and when this leaves, the configuration of this carbon actually inverts, because you see, suppose these groups were like this. Now when Cn minus is approaching, these groups are shifted, they are forced to shift in that direction. This hydrogen, as we know, is on the back side and this CH3 is on the front. We know that we can take these two bonds in a plane and this will be away from us and this will be towards us. So when the nucleophile approaches, these three bonds are forced to be in a plane, and when this leaving group leaves, these three bonds will go away from the nucleophile. So it is kind of an umbrella. That is, when you open it, it becomes planar, and then what happens to the umbrella is it becomes like this if you push further. So earlier the umbrella was this way. When you pushed it, the umbrella became something like this, and when you further pushed it, the umbrella became something like this. So we can see that at this particular carbon there is a kind of inversion, and that is a very, very important stereochemical aspect of this reaction, that in SN2 mechanism the configuration of this carbon is inverted, and we know that if it is a chiral carbon, then we can have a conversion from R to the S configuration. So let me complete the reaction. Here the final reaction would be, the final product would be C, hydrogen, C and this Cn. So you see that this product has formed if we start from this. Now what is the difference over here is that this hydrogen has actually gone back, this CH3 on the front and these two in the plane. If you write the nomenclature, you will find out that the stereochemistry has changed, that is the configuration has changed from R to S or whatever it is, S to R, if it is a chiral carbon. And if we take this thing some C2H5, it does become chiral, and hence the nomenclature has actually changed. And if it is not chiral, then simply we say that the configuration is changed or the configuration is inverted. So a very important aspect regarding SN2 mechanisms is the inversion of the carbon, and this defines, and with this we finish up the two mechanisms for the SN1 and SN2 reactions. Now let us further go in detail about this substitution reactions, because till now we have just studied what are these SN1 and SN2 mechanisms. Now we need to compare these with the elimination methods, that is when the elimination product is favorable and when the substitution product is favorable. So this comparison has to be made, but before that we will see one reaction in which the reaction is kind of nucleophilic, but it is not SN1 and it is SN2 only, but with retention of configuration. That is, if the retention of configuration is occurring, it doesn't mean that it has to be SN1, or in other words you can say that if there is no inversion of configuration, it doesn't mean that the reaction is not SN2. It is possible that you have an SN2 reaction, but still the inversion of configuration does not take place. And such reactions are also called pseudo SN2 reactions. Why? Because they look like they are SN2, but inversion of configuration does not take place. And the reaction is, we have already seen it, in fact, that we have seen in this lecture itself. The reaction we will see is ROH plus SOCl2. Now here we will see that although this reaction looks like SN2, but this is SN2 reaction without any inversion of configuration, or you can say with the retention of configuration. So we call this as SN1 reactions with retention of configuration. Now how does it take place? So we know the product RCl, definitely RCl, fine. What is the mechanism? To understand how the retention of carbocation, how the retention of the configuration is taking place, we need to understand what is the mechanism. Mechanism is very simple. Suppose you have this ROH and you have SOCl2. What is the structure of SOCl2? Cl and Cl. You can very easily draw through the Lewis structures even if you don't know the structure. SOCl2 is this kind of structure. Now what happens? Generally in substitution reactions, what is the first step? That a nucleophile attacks the carbon atom and you get a substitution product. But in this case, exactly the reverse happens. That is, the reaction or the reagent or the reactant attacks the reagent instead of the reagent attacking the reactant. So now first the reaction which happens is we have the lone pair of oxygen attacking the sulfur atom, and that gives us ROS. And what do you think is going to happen if there is an attack on sulfur? Clearly this sulfur cannot occupy one more bond and this chlorine atom happily leaves. So sulfur double bond O, Cl plus Cl minus. Now what is the next step? How do we get RCl? Definitely this is a nucleophile and this is a positive carbon center, because this RO bond is also kind of polar bond and actually it is more polar than the alkyl halides. So we have here RO S double bond O Cl, S double bond O Cl. Now these three groups are as it is. In ROH, if there is only one bond, these three groups are as it is, these three groups are as it is. So that is why the retention of configuration takes place. That is, the nucleophile now comes on the same side and attacks this carbon. It doesn't come from the back side. We saw that the inversion takes place because the nucleophile came from the back side and attacked, and hence the groups have to be going to the other side to avoid the repulsion. But here there is no such problem because this Cl minus is attacking from the same side where the leaving group is present. So Cl minus comes and attacks and this leaves. So hence we get RCl and we have this thing. So you see how retention of configurations take place. In fact, there is no carbocation production over here, kind of SN2, but still without the inversion of configuration. We get this product, very happy. Now let us move on. Let us see one more example of the same type where the reaction is SN2, correct, but there is no inversion of configuration. There is a retention of configuration, but it is different from the example, the SO2Cl2, the SOCl2 example we have just seen. Let us see how it is different. We can consider something like this kind of groups, and there are some groups like this. The tetrahedral carbon has 4 groups and 2 groups like this. Now here what happens if I just provide some heat? What happens here is the OH actually, okay, just provide some solvent without any heat. If you provide heat, actually here elimination can take place. Now solvent, this O atom has got lone pair of electrons. So now we know that this bond is quite polar, delta plus, delta minus, and we also know that oxygen has got some lone pair of electrons. So there is a nucleophile available to us, there is a carbon center which has got some deficiency. So what do? We have a nucleophilic attack there. We do not need an external nucleophile, we have an internal nucleophile itself. So this kind of plus H, and we have, that's it, this Cl which leaves when this O attacks. So finally we have the production of Cl minus also. Fine. Now we have got the positive charge on oxygen that can be very easily neutralized. Just take some base and abstract this hydrogen. So this hydrogen is also gone. When with that, the positive charge on the oxygen is also gone. Now this was a nucleophilic attack on a carbon, and we know that this is a perfect SN2 reaction, and because it is attacked from the back and the leaving group is on this way, and since it is attacked from the back, there will be an inversion of configuration. So how many inversion of configuration are taken place? There is only one single inversion of configuration. Now what happens? Now what happens over here is, we have this Cl minus, it can again attack over here, or we have this B minus. If the Cl minus again attacks over here, we get the same product back. But what if, in fact, if we have B minus? If this B minus attacks at this carbon, why should it attack at that carbon? Because this is delta negative, this is delta positive. Now this can also attack on this carbon, but then what we are trying to achieve will not be achieved, because we are trying to show that there is a SN2 reaction taking place, but without any inversion of configuration at this carbon. This reaction is equally possible, that is, this base can attack this carbon also, but then there will be inversion of configuration in two carbons. But if we attack this base over this carbon, this has a delta plus center which is having positive charge, and we have a nucleophile. So if we attack over here, it will be a SN2 reaction, and again we will have an inversion at that center. So we have got two inversions, and we know minus into minus is plus. So again we get the same configuration back at the carbon. Suppose the configuration at carbon was R, if it is chiral, and then it converts to S after the attack of this oxygen, and again it converts back to R after the attack of the base. So now what we see is our final product can be OH, B, and the two groups on this carbon. So this carbon has actually got its configuration back after two SN2 attacks. So you see that there is an SN2 reaction, but still there is no inversion of configuration. But the mechanism or the process is slightly different from the previous one. In this, there are two SN2 reactions, and in that the SN2 reaction was there, but it was from the same side as the leaving group. So we don't have any inversion of configuration. So these were some aspects of the SN2 reaction which are needed to be discussed, because SN2 reaction always does not mean that inversion in configuration. SN2 reaction means inversion of configuration if it is taking place once and the attacking group or the nucleophile is coming from the opposite side of the leaving group. If it comes from the same side, there is no need of any inversion. So now let us discuss something more in general about the substitution reactions, not particularly for SN2, not particularly for SN1. We will discuss some portions or some factors which affect the substitution reactions in general. So factors that affect substitution reactions in general. Substitution reactions in general. First, what is the factor that can affect this substitution reaction the most? The reactant. We have the reactant, which is an alkyl halide, and that is the best factor which can affect the reaction. If you change the halide, the reaction may differ, it can become slow, it may not happen at all, or it can become faster also. So first is the alkyl group in the halide. Fine. what can be the other possible factors that can affect the substitution reactions. The other factors are obviously the nucleophiles, the leaving group, and there are some more factors which are not clearly visible, but still if you apply a bit of thinking they will become quite obvious to you. Nucleophile, here we consider the structure and reactivity. Now we have a leaving group. Another case. Now, so these three are very obvious. We have a leaving group, we have a nucleophile, and we have the alkyl group. These three are very commonly observable reactants or the reagents. But what are other factors that can affect the substitution reactions? The other factors include the concentration of the nucleophile. Concentration of the nucleophile. Now, how does this affect the reaction? We know that rate of the reaction is dependent on the concentration of the species present in the product, species present in the reaction mixture. So that means if the nucleophile is present in the reaction mixture, then the concentration of this nucleophile does matter. And we know that in SN2 mechanisms, there are two products, it is a bimolecular reaction, and hence there are two species, one is the alkyl halide and one is the nucleophile which is involved in the order of the reaction. What are other possible factors that can affect this substitution reaction? What about solvent? If you see, the solvents play a very major role. We haven't seen the roles till now, but I think there is one reaction in which we have seen the role of solvents. You remember the displacement of chlorine with iodine. In this case, we saw that the solvent acetone plays a very important role. How? That NaCl is not soluble in acetone while Na is, and hence this precipitates out of the mixture, and hence the reaction completely propagates in the forward direction, and you get quite a good yield of the iodide, alkyl iodide. Fine. So this was just a role of solvent, but this kind of role is not observed in the substitution reactions. What kind of roles are observed, we will discuss when we go to the solvent part. So the solvent, and finally chemical reactions, almost all of them are affected by temperature. This is a very common factor in almost all of the chemical reactions. So temperature is inherently present here. So let us discuss this one by one. Alkyl group present in the halide. How can it affect the rate of the reaction or course of the reaction or whatever? Now, if the alkyl, what are the different alkyl groups first of all thing? For understanding how it affects, we need to understand what are the different alkyl groups. So, we have phenyl, we have normal simple open chain alkyls, we can also represent it by R group, and we normally represent it by R group. Then we have got vinylic, we have got allylic, and in R group, which is normal open chain, we have got primary, secondary, tertiary. So let us see how these groups affect the nucleophilic substitution reactions. Fine. What about, first let us forget about these three. Let us consider primary, secondary and tertiary. We have a primary group C and it is connected to something. We are focused on this carbons which has got these three hydrogens. Now this is a primary carbon or a primary halide. Now if you want to compare the rates of reaction of this and this one, then let us compare. Primary halide, secondary halide, tertiary halide. We have got two mechanisms and let us consider both the mechanisms separately. In SN1 mechanism, what is a possible factor that can affect the rate of the reaction or it can make the reaction go in the forward direction faster? As we know that there is a carbocation intermediate forming in that reaction, and if we can lower the energy barrier for the formation of that carbocation, we can definitely proceed the reaction in a more faster manner. Now, which is the most stable carbocation? Tertiary, secondary, primary? Obviously tertiary. So hence, in case of SN1 mechanism, that is, if the SN1 mechanism is followed, or if we take the SN1 mechanism. Actually, SN1 and SN2 both will happen in a reaction mixture. Suppose you take some alcohol and some HBr, then in that case SN1 mechanism and SN2 mechanism, both the pathways will be followed. That is, we have the mixture over here, there are some suppose 100 molecules, then suppose some 20 molecules will go for SN1 and 80 molecules will go for SN2. So these two will happen simultaneously, but the major product we are talking about, that is, we get SN2 as a major product or SN1 as a major product. In this case I have just taken an example, and it so happens that SN2 is the major product. So we need to find out what are the factors that affect whether the reaction should go towards SN1 or towards SN2. But before that, we need to see SN1 and SN2 separately, because there are two different pathways and there are different mechanisms involved, there are different intermediates formation. In this case there is only a transition state formation. So first we consider them individually and then we compare them, and finally we will compare the substitution reactions with the elimination reactions. As I told you, these are two competing quantities. So again we will say 21 towards the elimination and 80 towards the substitution. So again, what factor decides these numbers we have to study after studying these two, and then comes the third one. So you see how we are going to proceed, and let us proceed. So we have discussed tertiary, primary and secondary. In case of SN1, what is the reactivity order? What happens if it is SN2? Now in SN2 what happens is, we have a nucleophile and a leaving group. This X is a leaving group, and this nucleophile has to approach this carbon in a fashion such that it is opposite to the leaving group. Now if it is a tertiary halide and this nucleophile has to approach this middle carbon, it has to approach this middle carbon, how will it approach? It will try to approach from the back side, but as you can see there are three big CH3 groups which are standing on the way to the nucleophile and the carbon, and they will definitely hinder towards the reaction. But what happens in case of a primary halide? We have got only two hydrogens and one carbon, and they will say okay fine, these two hydrogens will easily let the nucleophile attack the carbon. So that means in SN2 case the order is just the reverse, this way and this way. So in SN2, primary halides are very much reactive towards SN2, followed by secondary, followed by tertiary. Tertiary are the least reactive, but they are quite some reactive. Major amount will go towards the SN1. We will try to go towards the SN1 in case of tertiary. So if we want to compare now SN1 and SN2, we have considered SN2 separately, SN1 separately. Now let us compare SN2 and SN1. SN1 and SN2. Now suppose it is a tertiary halide. We know that carbocation formation is quite stable, and we know that it is hindering the SN2 reaction. But now we have to decide now which will go first. These two factors suggest that it should go towards SN1. Carbocation formation is stable and it is hindering the nucleophile attack in case of SN2. But we have not seen all the factors which affect the reaction which affect the substitution reactions. So right now we cannot tell whether it will go towards SN1 or whether it go towards SN2 or whether it goes towards the elimination reactions, because apart from the substitution reactions there are elimination reactions, and if you change the reaction condition slightly, that is if you raise the temperature, if you decrease the concentration of the nucleophile, then in fact elimination will be the major product as compared to substitution, and in substitution in that case SN1 will be the major product as compared to SN2. So that discussion we will have later on. Let us move on to the phenylic and vinylic and allylic halides. Now this phenylic, vinylic names are we have heard before, but what is allylic halides? Allylic halides are actually this type of halides, X or Cl, whatever. There is a double bond and on the beta carbon there is a halide. Now I have already told you this, that this is not a vinylic halide because it is attached to a sp3 carbon, but the carbon is actually followed by a double bond. So it has got some special character, and definitely it is different from a simple halide like this. In what ways it is different? We can easily understand in what way it is different if we compare the reactivity towards SN1. Now, SN1, what is the first step? That is the formation of intermediate. So we need to compare the stability of the carbocation in the two cases to understand what is the effect of the vinylic, the allylic and the normal alkyl halide. So, if you form the carbocation in this case, we will see that this carbocation is like this. This carbocation forms over here. What is the difference between the two carbocations? Actually, both are on sp3 carbon, but this carbocation is resonance stabilized. If you want to draw the resonance structure, you can draw the resonance structure as this. So now the second or the allylic carbocation is resonance stabilized, and hence we can conclude that the allylic halides will be more reactive towards the SN1 reaction as compared to normal alkyl halides, and in fact they will be definitely more reactive towards the SN1 reaction as compared to the tertiary halides also, because here it is just the stability of carbocation through inductive effect and hyperconjugation, but over here we have the stability of resonance coming in the picture. Fine. So that was allylic halides. Vinylic and phenylic halides. Is nucleophilic substitution feasible in these two? Let us see. Let us see whether nucleophilic substitution is feasible in case of phenylic or vinylic halides. X, C double bond C, X. I am suggesting that actually this nucleophilic substitution won't even occur in these two halides. Why? Why? Because let us go one by one. SN1 mechanism. If it goes by SN1 mechanism, then we get a species which looks like this. This resonance is gone, aromaticity is gone. We have a positive charge over here. We have a double bond here. We have a double bond here. Although the carbocation is resonance stabilized, but you dare not say that this is more reactive than the alkyl or the allylic halides, because this is stabilized on the cost of the loss of aromaticity. If the aromaticity is lost, then even though this is resonance stabilized, it doesn't matter. It has already incurred a very huge loss, and hence it does not undergo the nucleophilic aromatic substitution. And here also in this case we will get a positive charge over here, and this is sp2 carbon, and sp2 carbon is more reactive than sp3 carbon, and this also is very unstable carbocation, and here also the nucleophilic substitution will not take place. But the good news is we are going to study a class of nucleophilic substitution reactions for aromatic compounds with some special reagents at the end of this lecture. So just be happy that actually nucleophilic substitution takes place in aromatic compounds, but it is very rare in vinylic compounds. Fine. So we have seen that how alkyl group actually affects the reactivity towards SN1 and SN2 reactions. Fine. What was our next topic? The next was the structure and the reactivity of nucleophiles. If you see nucleophiles, they are nucleus seeking centers, and what factors can affect their structure and reactivity? Definitely it is the nucleophilicity, and nucleophilicity is determined on what basis? It is determined on several factors like charge, basicity, size also. So nucleophiles, we have charge, we have basicity. Remember, basicity is not same as nucleophilicity, although nucleophilicity depends on the basicity order. It is a factor, it is a very significant factor to affect the nucleophilic properties of the nucleophiles. But these two are completely different concepts. I have already explained this thing and I am not going to explain it again. The charge, basicity and the size. Now how does this size matter? I mean, nucleophiles are what? Electron donors. How will size matter on that? Size matters because the electron density depends on the volume of the atom also. Remember, density or the charge density is the charge per unit volume. If the charge is more, that means the electron density is more diffused and hence it won't be a good nucleophile. For example, F minus and I minus. We can say that in I minus the electron density is more diffused and it is a weaker nucleophile than F minus. Although this order can also be explained in terms of basicity, that HF is a very weak acid as compared to HI, and hence F minus is a very strong base and hence F minus is a very good nucleophile. So in this way, using these three factors you can actually explain the nucleophilic properties. But unfortunately the story doesn't end over here. We have a very important role of solvents over here, and we will study this role when we go to the solvents part. Now let us continue with our nucleophilic story. In the nucleophilic story, we will just explore a little bit charge. What do I mean by nucleophilic properties are affected by charge? If you see, a charged molecule is definitely a better nucleophile than an uncharged molecule. What do you think about NH2 minus and NH3? Now these are conjugate acid and conjugate base pairs, and definitely this must be the better nucleophile, can be explained on the basis of both charge and basicity. And if you want some more examples, NH2 minus, H2O. These are not acid base pairs, but still you can explain them on the basis of the charge properties. That is, a charged nucleophile is definitely better than the neutral molecule. Fine. This was a simple explanation of charge, how charge affects the nucleophilic properties. But what if we have the same charge? For example, Ro minus and C minus. You can take anything, another carbon. Fine. Now, which of these two are more nucleophilic in nature? We have the same charge. Now, how do you explain? We can take the order of basicity, and if you take basicity, then definitely this is much more basic as compared to the Ro minus, and hence this is much more nucleophilic than compared to Ro minus. But if you apply one logic over here, that O is a more electronegative atom, true, and hence O should be having a tendency like it can hold the negative charge better, and so it can donate better. So if you apply that logic, there is a slight mistake in that. What you are saying is O is more electronegative and hence it can hold the charge better, then why should it donate the electrons? If it can hold the charge better, let it keep itself, and carbon cannot hold the charge and it donates. So if you see through electronegativity prospect also, we will get the same order. But if you see through basicity, then we get a stronger point that this is much more basic and we get the actual order. Fine. Now we have seen basicity. Size we have already seen, I minus and F minus. But that I minus and F minus, that order is reversed in case of polar and non-polar solvents. As I told you, the story didn't end over here. It will continue when we will discuss the solvent part. Fine. Now let us move on to the next one. What is the next one? Next one is something about the leaving group capabilities. Fine. Wait a second. We have discussed nucleophiles. We have discussed which is stronger nucleophile than the other, but we haven't discussed what is the effect over the substitution reaction. The substitution reaction, the effect is, if more stronger the nucleophile is, the better, the faster will be the reaction. Because if suppose we have this carbon, if the nucleophile is weak, then what can happen is the reaction can also go in the backward direction. And if this incoming nucleophile is weaker than the leaving group, then definitely you won't get any significant amount of product. Everything will go towards the backward direction. The whole reaction will be reversed. So that is very important factor which it is affecting the substitution reactions. Fine. So let us now see leaving group. Leaving group, clearly the effect is the better the leaving group, the better will be the reaction yield and the faster will be the reaction. If the leaving group is not good, then we will have to apply a stronger nucleophile and hence the reaction becomes a bit complicated. I mean, the reaction is not simple in that case. If we have a good leaving group, the reaction can happily take place with weak bases. But if you have to take a stronger nucleophile, you have to select a nucleophile as strong as amide ions or something like that. Suppose CF. In case of CF, we generally have this problem because F is a very bad leaving group, and if you have to displace this F, then you have to apply a strong base, suppose carbon or even amide ion will do here. Fine. So what are the characteristics of this leaving group? We have a general idea about the leaving group, that the leaving group properties are in fact inversely proportional to the basicity. Yes, and that is the only idea of the leaving groups. If you want to see how it is so, if the compound is more basic, then what happens is, if we have a leaving group, suppose OH minus, and we have a leaving group H2O. Now, which is a better leaving group out of these two? That means if we have OH like this and we have OH2 plus like this. Now, if this is a leaving group in the molecule, it must be having some charge or O plus here, so that the carbon can donate the electron density like this. If it is O minus here, this must be having some charge OH, which is in neutral here, so that it can take electron density and it can get a negative charge. Suppose you have here a lesser electronegative atom than carbon, then in that case, suppose that atom is B, this is not boron, but just some general atom B which is less electronegative than carbon, then the bond cleavage will be in the opposite direction. And if you have B as a leaving group, then you must be having B minus as your group which is directly attached to the carbon, so that the electron density goes over here and you will get C plus B. Fine. So what determines the leaving group properties? We have seen basicity and we have also seen how it is so. So this is obviously a very good leaving group, actually a much better leaving group as compared to OH minus. And we have already seen what is the effect of the leaving group on the nucleophilic substitution reaction, that the reaction goes faster and you have a better yield of the reaction. The reaction doesn't become reversible. Now the solvent part. Yes, now comes the solvent part, and which is very important. This nucleophilicity and leaving group thing is just general idea. There is nothing specific about them. The definition itself says all the factors or all the properties of these, but solvents, it is somewhat complicated case. So if you have solvents, how do they affect the SN1 and the SN2 reactions? So now solvents can be divided into protic and aprotic solvents. What is this protic and aprotic solvents? Protic solvents, for example H2O, have got a hydrogen which get involved in hydrogen bonding with the other molecules, or which can solvate a carbocation, solvate electron deficient species. Those are called the protic solvents. Aprotic solvents are just the reverse of protic solvents. For example, you consider benzene. Here you consider water. Now this is completely aprotic solvent, and these are also called non-polar solvents. Protic solvents are also called polar solvents. Fine. So how do they affect the SN1 and SN2 reactions? They affect the SN1 and SN2 reactions by affecting the nucleophilicity of the compound. Nucleophilicity. Now, this is the case with SN2 reaction, because we know that the only transition state is forming and there is no intermediate formation. But suppose we have SN1, then in that case they also affect by considering the carbocation case, because you know the slowest step in that case, in SN1 case, is the carbocation formation, and if the carbocation is becoming more stable due to some reason. It can be rearrangement, it can be the solvation due to the solvent, or it can be any other reason. So if any reason stabilizes this carbocation, then we will get a better yield and a faster reaction. And nucleophilicity is major for SN2 reactions. Although here also there is a nucleophilic attack, but remember that is not the slower step. Carbocation formation is the rate determining step in case of SN1, and in case of SN2 the attack of nucleophile is obviously the only step in the mechanism. Fine. So how does these two affect? First of all thing, let us say nucleophilicity, because carbocation is kind of quite obvious. Now how does it affect nucleophilicity is, if we consider F minus, Cl minus, Br minus, I minus. What is the nucleophilic order of these molecules or of these ions in a protic solvent, suppose H2O? Tell me what is the order. I have just now told you that F minus is a better nucleophile when compared to the I minus. So that means, as you know, halogens are also kind of homologous series. They have also got that chemical property same and kind of gradation in the properties. So what do you think will be the order? Most probably the order will be like this, because F minus is greater than I minus. So the order must be this. But in fact you are wrong. F minus is a weaker nucleophile in a protic solvent as compared to I minus, and the observed order is, this is wrong, and the observed order is, let me remove some part, F minus lesser than Cl minus, lesser than Br minus, and finally lesser than I minus. So how is that order coming, and how can you actually explain that order? That can be explained by this protic solvent properties. Protic solvent actually have the property of solvating the molecules. We have seen somewhere that Li plus and Cs plus, which is more hydrated, Li plus or Cs plus? We know that Li plus is more hydrated because of the charge density as compared to Cs plus, and hence Li plus, the size is bigger as compared to the Cs plus, whose size is smaller. Similar thing happens over here. Here I minus is very less solvated, Br minus is more solvated, Cl minus is even more solvated, and F minus is the most solvated case, and hence the size matters over here. That is, the size of F minus is the biggest, and hence it is a very weak nucleophile. But here I minus is having the smallest size, and it is the best nucleophile possible among these four. Now what about the case in aprotic solvents? Aprotic solvents, this is the observed order, because there is no solvation and you have normal basic properties, that is, it completely depends on the basicity. Nucleophilicity completely depends only on the basicity. What happens in gaseous state? Suppose these were not present in any solvent, the substitution reaction is present in the gaseous state, that is, there is no solvent present. Then in that case what happens is, again this order is followed, because in gaseous state the only property which you can observe is the basicity, or more properly the size of this. The size of this is very small as compared to I minus, and hence the density is more in case of F minus, and it is a better nucleophile. So you see that how solvents can play a very important role in case of the substitution and these reactions, and they also stabilize the carbocations, and carbocations are stabilized by protic solvents, and if they are stabilized more, the reaction will go faster in case of SN1, and in a protic solvent that will be quite slower, the same reaction. Now finally we have discussed all the properties of these, all the factors which affect the substitution reactions. That means we have covered what factors determine SN1 separately, SN2 separately, and we have also considered some factors between SN1 and SN2, that is, which factors are favorable for SN1 as compared to SN2, and which factors are favorable to SN2 as compared to SN1. But now it is time to compare the substitution and the elimination products. Now these factors, whatever we have discussed, will actually help us in doing the comparison between substitution and elimination. Now If you have to compare two processes or two reactions, you cannot compare arbitrary processes or random reactions. We know that SN1 and E1 have got similar mechanisms and hence we can compare them. But if suppose you want to compare E1 with SN2, they are actually quite different reactions, or not different, they are different reactions, even SN1 and E1 are different reactions, but their mechanisms are quite similar. But E1 and SN2, their mechanisms are very much different. E1 involves intermediate formation while SN2 involves just a transition state formation. So hence we cannot compare E1 with SN2. We compare like with like and another like with another like. So we compare E1 and SN1 and we compare E2 and SN2. So that will make sense. Comparing E1 with SN2 and SN1 with E2 has got no sense actually. So let us start the comparison. E1 SN1 and E2 SN2. And definitely the factors which we have discussed and the mechanism will clearly tell us what will give which product under what conditions. So E1 versus SN1 and E2 versus SN2. SN2. So I will write primary halides, secondary halides and tertiary halides. We have already seen the difference between these three together in E1 and E2 and in E1 and SN1. But if we consider this category alone, that is primary halides, then what are the differences between E1 and SN1? Now, primary halides, what are the advantages, what are the factors that can favor even reaction? Even reaction involves carbocation formation, and we know that primary carbocation is not so much stable, and even if you want to rearrange, then it becomes a kind of secondary halide. Then it comes under this category, that is we have a secondary halide. So mostly primary halide will undergo the substitution reactions or the SN1 reactions. Sorry, not even SN1 reaction, because SN1 reaction also involve the carbocation formation, and so that is why primary halides will neither favor the SN1 reaction or the E1 reaction, but it favors the E2 reaction and SN2 reaction. Now, out of E2 and SN2, which do you think the primary halide will favor? What is the E2 reaction? E2 reaction involves transition state, something like we have Br and we have a hydrogen here, we have a base is forming a bond, this is forming a bond, this is forming a bond. Now this E2 is actually not, the steric hindrance from this carbon does not affect base, because the base is coming from the side which is favoring this carbon. That is, if there is more steric hindrance over this carbon, then the reaction would be slower, and hence the E2 and SN2 both are preferred, because the steric hindrance due to this carbon matters and not due to this carbon. So based on this, whether this is having bulky groups or based on this base, whether the base is bulky, we will have either E2 or SN2. If both are small, then we can have E2 at higher temperatures, but if both are quite small in size, then we can have SN2 at lower temperatures. If we go for higher temperatures, then elimination reactions in general are favored over substitution reactions. Fine. So this was primary halides. We discussed that E1 and SN1 are not so much favorable because they involve the production of the carbocation, but E2 and SN2 are very much favorable for the primary halides. What about secondary halides? Secondary halides, the carbocation is quite much stable, considerably stable and much stable compared to primary halides. So what do you think is the possibility? E1 is better or SN1 is better? Now E1 and SN1 depends on this, plus SN1 there is thing like the strength of the nucleophile also, or if the strength of the nucleophile is more, then the reaction will proceed in the forward direction more, and E1 we depend on the strength of the base. So hence it depends clearly whether the species present in the mixture is a better nucleophile or it is a better base. So depending on that, and clearly solvent plays a very major role over here because that determines the nucleophilicity properties. So if it is not nucleophilic, so then the elimination will occur because then it is more basic in nature. But if it is nucleophilic, then we can have the SN1 reaction. So hence, and temperature is again a very important factor over here. At higher temperature, even and with strong base, and you can say less bulky base, more bulky base. If it is a lesser bulky base, then in that case what happens is it goes for the SN1 reaction. Less bulkiness and lower temperatures as compared to this. So we see that these are the possible conditions, and if there is a bulky base, then mostly it will go for the hydrogen abstractant instead of attacking this carbocation. Fine. And if it is a stronger base, then more nucleophilic properties, then it goes again for the hydrogen abstractant, and if it is a stronger nucleophile and not that strong base, then it goes for the SN1 reaction. No doubt about it. What about E2 and SN2? Now this E2 and SN2 depend completely on the nucleophilic properties. That is, if there is steric hindrance, then definitely E2 is preferred. If there is lesser steric hindrance, then SN2 is preferred. So in secondary halides, we will usually get a mixture of products. We will get even products also, E2 products also, and E1 and E2 products need not be same because we know that the secondary carbocation can rearrange to a tertiary carbocation. So hence we can have E1 and E2 isomeric products, and we can have SN1 and SN2 isomeric products. Both E1 and SN2 will not give isomeric product because E1 is elimination reaction and you get an alkene, and SN1 you will get some other compound like OH or CN, something like that. So these two will not give you isomeric product, these two will give you completely different products. Fine. What about tertiary halides? Now this is again a very similar case to primary, but in this case the reverse happens. In tertiary halides, we almost never observe the E2 and SN2 reactions. Why? Because it is so much heavily crowded that the base or neither the nucleophile is able to come near it and hence attack it. So we have mostly E1 and SN1 reactions, and the same factors apply over here, that at higher temperatures you will have mostly the elimination product, and at lower temperatures you will have SN1 product. And it also depends on the bulkiness of the base. If the base is also bulky, then definitely it goes for the E1 because SN1 we require, already the tertiary halide is very much overcrowded, and if you have a bulkier base, then it becomes very difficult to donate its electron density. It is much more easy if you can abstract a hydrogen from one of the carbons surrounding the tertiary carbocation. So you see the comparison between E1 and SN1. Everything plays a role: nucleophilicity, basicity, the role of solvent, and obviously the temperature. So all the factors which we have studied for the substitution reactions, which affect the substitution reactions, help us in determining the difference between even reactions and substitution reactions. So whenever you are given a reaction, please make sure that you take whatever the base is given and whatever the compound is given, you choose a proper reaction, either elimination or substitution. It is sometimes asked like this: you will be given a question and you will be asked 3 products or 4 products. Now in that case, what you might do is you take each and every reaction. Suppose secondary halide is given and you are asked 4 different products. Then you consider E1 product also, SN1 product also, E2 product also, and SN2 product also. It depends on our consideration also. Suppose we want just the E2 product, we will write just the E2 product. Suppose we want both E2 and E1 products, we will write both E1 and E2 products. But remember, while writing the products, be careful, write the mechanism properly, write the intermediate stability properly, and follow the final Hoffman or the Sergev rule in case of elimination reactions, although there is no such rule in substitution reactions, but please see that about the stereochemistry in SN1 and SN2 reactions, and especially SN2 reactions, that inversion of configuration and retention of configuration of carbon. So this was it, the elimination and substitution reactions, a huge topic. Now we were discussing, when we started this subtopic, we were discussing the chemical properties of alkyl halides, and from then on we have been discussing just the substitution and the elimination reactions. But there are obviously other chemical properties, and all of them we have discussed. Fortunately, we have discussed all the other chemical properties of alkyl halide. We have Wood's reaction, which is a reaction of alkanes, that is, you take two different alkyl halides, you put them in Na and ether, and you get an alkane. That is Wood's reaction. That is a preparation reaction for alkane. And then we have dehydrohalogenation, that also we have seen. So these two reactions were the remaining reactions, and you also have the reduction of alkyl halides, which is also preparation of alkanes. So you see, the preparation of the alkanes and alkenes, most of the chemical properties of alkyl halides are covered except the substitution reactions. So this was it. Now we consider a special reaction of alkyl halides. There are two typical reactions of alkyl halides. One is substitution and another one is that we are going to discuss. Production of Grignard reagents. Now these Grignard reagents are organometallic compounds. That is, we have a bond between the carbon atom and the metal atom of the reagent, or metal atom, suppose magnesium and lithium. These are the most common reagents, these are the most common metal atoms which will form bonds with carbon when we discuss the Grignard reagents or organometallic reagents. Now this lithium reagent we have seen once in Korehouse synthesis. What is this Korehouse synthesis? We have R2CuLi, and this is used in the preparation of alkanes and is a very important reaction, because this gives almost 75% yield of the alkanes, which is a very good yield in organic chemistry. Generally 40% itself is considered a very good yield, but 75% is huge. Now Grignard reagents, first of all think how to prepare them, and then we will start discussing the properties. You basically take an alkyl halide and you put them in a mixture which contains magnesium powder, and the solvent is ether. Ether, as we know, is this kind of linkage is present. We have a C, single bond O, C. So this is called an ether, which is a non-polar solvent. And if we react this mixture, what do we get? We get something called RMGX. That is, the structure of this is R minus, Mg2 plus and X minus. So this is a reaction, this is a bonding present, and now what are the possible reactions that it can undergo? What is this species? R minus, that means it is a carbocation or a carbanion, and it is very reactive. If you have any acidic hydrogen which is present in the molecule, it will simply abstract that. Just like that, it will abstract it without seeing anything. It is a very vigorous reaction, and that is why this Grignard reagent should be kept away from the moisture, otherwise they will be destroyed. And they can only be used in non-polar solutions, they cannot be used in polar solvents. For example, Grignard reagents can be used in NaBH4 but not LiAlH4. Now NaBH4 and Grignard reagent, there is a reaction which we will discuss later, but LiAlH4 and NaBH and RMGX should not be used together, because this will dissolve in polar solvents, and if you try to dissolve it in polar solvents, that's all, your reagent is gone. You won't have no longer the Grignard reagent. So let us see some reactions based on Grignard reagent. One basic reaction is the production of alkanes. Now this we have seen in the advanced level of alkanes. I have given you one question in which there was some product, some alkyl halide or something, and there was Grignard reagent. So not alkyl, alcohol and a Grignard reagent. And I asked you what is a possible product. So let us see again. We have Cl, we are putting it in Mg ether, and finally we are treating it with suppose H2O. What is a possible reaction in this case? What the reaction we get is, first we get a Grignard reagent which is C minus, Mg2 plus and Cl minus. Now if you treat this with H2O, we know that this hydrogen is enough acidic so that the Grignard reagent can abstract it. So now what we get is a alkane or a propane. So now you can see this is another chemical property of alkyl halide, that if you start with propyl chloride, you can produce propane from that using Mg ether and any acidic solvent or any polar solvent. Now instead, if you have something like alcohol, now this hydrogen is very acidic and even Grignard reagent can abstract this. Why are we taking alcohol? Let us take alkynes. Even if you have alkynes, this Grignard reagent can abstract this hydrogen also. It is that much basic in nature that it can abstract the alkyne hydrogen, and we know this is very weakly acidic, but strong enough acidic so that the Grignard reagent can abstract it. Fine. Now there are some more reagents of some more reactions for Grignard reagent. Let us see one of them. These Grignard reagents will be very frequently coming when we discuss alcohols, preparation of alcohols, chemical properties of aldehyde ketones and carboxylic acids and derivatives, and in those chapters. Suppose we have a Grignard reagent C minus, Mg2 plus, X minus. We treat it with an alcohol or a carbonyl compound. This is what? This is acetone, and we treat it with a Grignard reagent. What do you think is the product? Right now I am not going to tell you any mechanism for this reaction, I am just going to tell you what will be the product. The product will be, after hydrolysis, first step is the Grignard reagent, second step you need to hydrolyze it. So the product would be a tertiary alcohol. So you know that when ketones are reacted with Grignard reagents, they give you tertiary alcohols. It is very important that you know this reaction, because this is very important chemical property of ketone and a very important preparation method for alcohol, because the yield is high, everything is very high, and this is a very important reaction. So this is one example of the chemical properties of Grignard reagent other than the basic property. Here you see there was no acidic hydrogen available and the Grignard reagent reacted in some other manner, which I am not going to discuss over here because this will be discussed in the aldehydes and ketones chapter. So this was Grignard reagents. So with this we finished the alkyl halides part. That is, we have discussed all the possible chemical properties as well as the physical properties. Now it's time that we go towards the aryl halides. Now these aryl halides, as we know that these are not going under any kind of substitution reactions. So what reactions are they going under? We know that these won't go under nucleophilic substitution reaction. Nucleophilic substitution reaction. So what reactions can these undergo? That depends on the structure of the aryl halide. Let us just have a small look at the structure of this halide. Now what we have over here is, we have an aromatic carbon chain, a 6-carbon member, a benzene ring with a hydrogen substituent. So now what is available with the benzene ring? Benzene ring has got a pi electron cloud above and below its plane. So that means it has got pi electron density with it, and that means it can donate its pi electron density. But it just like that does not donate its pi electron density. We have special mechanism for it, and we are going to discuss that mechanism, and that mechanism is called electrophilic aromatic substitution. Electrophilic aromatic substitution. Fine. What is the meaning of electrophilic aromatic substitution? The meaning of this is substitution is taking place. It is aromatic in nature because we have aromatic compound. What is the meaning of electrophilic? Electrophilic means that if there is an electrophile available, then this benzene ring can donate the electrons into this electrophile and there can be some kind of substitution. Now that substitution is not the substitution of this alkyl halide, because if this alkyl halide has to be, if this halide, not alkyl halide, if this halogen atom has to be substituted, then we have to go for a nucleophilic substitution reaction. But we know that this benzene ring does not go under nucleophilic substitution reaction. They undergo something called electrophilic aromatic substitution, and the meaning of that is the benzene ring can donate its electron density into an electrophile, and what happens here is instead of the halogen atom, one of the hydrogen atoms are replaced. That means we get two isomeric products, one is this and another is this. So we see with halogens we get an ortho product and a para product. Ortho product because the electrophilic group is coming under the ortho position 2x, and this, in this case, the electrophilic group is coming under the para position 2x. So let us see how is this possible. What is the possible mechanism that we can write for such a reaction? And in fact we have two class of derivatives here, that is halides are one, we have alcohols, we have phenols. That is the electrophilic aromatic substitution is a property of phenols also, is a property of benzoic acid also, is a property of benzyl aldehyde also, and so on. So each and every substitution can undergo this electrophilic aromatic substitution, but with different characteristics. The rate of the reaction is different, the products of the reaction which are obtained through the reaction is different, and there are many more properties which we need to discuss in this electrophilic aromatic section. So first of all, let us discuss something, a very important term. Actually there are two important terms before we study this electrophilic aromatic substitution. There is a term called ortho para director and there is a term meta director. Now what are this ortho para and meta directors? That simply is, if the electrophile which is coming towards the benzene ring is added on the ortho or para position, the group, suppose the aldehyde group or the halogen group or the phenol group, is a ortho para director. But if the electrophile is adding at the meta direction or the meta position, then it is a meta director. So generally meta directors are aldehydes, because these deactivate the ring. How they deactivate the ring? They will take up the electron density from the ring, and we have seen how it takes up the electron density, and generally the deactivating groups are meta directors and the activating groups, for example alcohols, amines, are also para directors. To understand that concept better, let us draw the resonance structures and see. What are ortho para directing groups? They direct the electrophile which is incoming electrophile to the ortho para position or to the meta position. So if suppose I take a general benzene ring and a general group like this, when is this group ortho para directing and when it is meta directing? As I told you, generally the deactivating groups are the ortho para directing, deactivating groups are the meta directing, and the activating groups, that is the groups which activate the benzene ring, that is they donate electron density to the benzene ring, are the activate or the ortho para directing groups. So now for writing the resonance structures, I need to put these double bonds like this. Fine. Now suppose I have to donate the electron density from this benzene ring to the incoming electrophile. So what I do is I will write the resonance structures this way. This suppose I am donating over from here. This carbon is having some electron density, and if this carbon donates the electron density to the electrophile or the incoming electrophile, E plus, and I have donated the pi bond density to the E plus, and what I can write over here is the double bond is broken and a single bond or sigma bond is formed. As you see, we have a breakage of sigma bond, breakage of pi bond, and a formation of sigma bond, and we know that sigma bond is much stronger bond as compared to the pi bond, and hence it is a feasible step. But remember, while going from this resonance structure to this resonance structure, the ring is losing its aromaticity. So hence there are two opposite factors. One is the loss of aromaticity and one is the gain of energy through the breakage of pi bonds and the formation of sigma bond. So these two factors decide whether the rate of the reaction will be fast or slow and whether the yield of the reaction will be good or not. Fine. I have this and I will get a positive charge over here because this carbon has donated its electron density, and the normal Z is here. Fine. And sorry, this carbon does not get the positive charge, this carbon will get the positive charge because positive will shift into suppose positive and negative, then negative charge and donates the electron density to the electrophile. If you do this, then you have resonance structures like plus Z, Ze, then you have a double bond over here, and then you have Z. Another resonance structure can be positive charge will shift over here and the negative charge comes over here and the double bond comes over here and the double bond is over here, Z, and here we have E. That's all. Now over here we see that the carbocation which is formed is very stable because it is having 1, 2, 3 resonance structures, and finally that hydrogen is abstracted and we get a perfect benzene ring back again with the E substitution at the ortho position. Now suppose the E is substituted at the meta position. Now before that, if suppose that is a activating group, then it will donate its electron density into this and hence the positive charge would be stabilized because the benzene ring has now become electron deficient. It needs some supply of extra electrons, and if it is a donating group, suppose OH, if this Z is OH, then it has got the lone pair of electrons which can donate into the benzene ring and hence can stabilize the benzene ring further. Fine. We can also visualize the whole process in terms of, suppose I want to donate the electron density from here. So I consider a negative charge over here, OH over here, and this something like this. Even this is very much stable, and this is also stable then if we have some structure if the negative charge has a meta position. So either you can visualize that first the attack has happened and the positive charge is there, or you can also visualize in terms of the carbo anion. In both ways you will get that the deactivating groups are the ortho para directors, and you see even if it is the para position, the positive charge will be in such a way that the positive charge comes over here, and we know that the ortho and para positions, if the positive charge is coming, it is having more electron density, but here you see it is at the meta position with respect to this group, and we know that this has got less electron density and hence the positive charge is stabilized like this. Fine. Now let us consider if this incoming electrophile is coming at the meta position. That means our resonance structures will change a little bit. So they become something like here, and this electrophile is here. We can keep that bond, we can keep this Z, and we can break this bond. Now if we have broken the bond, the positive charge comes at the para position. In the previous structures, the positive charge, as you can see, was coming either at the ortho position or at the is coming at the meta position with respect to this group, or with respect meta position with respect to this group. It never came in the ortho or the para position. Why? Why if positive charge comes in the ortho or the para position, it is destabilized? That is because since it is an activating group, the electron densities at the ortho and the para positions are quite high, and hence positive charge is not stable at those two or those three positions, and that is why we don't have this electrophile coming at the meta position. It will come always either at the ortho position or either at the para position or at the two ortho positions. So this is the concept of this ortho para directing and meta directing. It just depends on the charge densities present at these three carbons. We know that deactivating groups will reduce the carbon density at these three carbons, and activating group will increase the carbon density or the charge density at these three carbons. So in case of deactivating groups, the ortho positions will be preferred and the para positions will be preferred because the positive charge is quite stable there. The electron densities are lower and hence the positive charge can come over here. That is why deactivating groups are meta directing and ortho and activating groups are also para directing. So that is it. With this simple example or with this simple logic of resonance structures, we can understand such an important concept. Now we can see some examples of this electrophilic aromatic substitution. One simple example is this. Suppose you consider we have got OH and we have got some HX. Now what is the possible reaction over here? Now the reaction over here is we need a electrophile, and the electrophile is H plus, and we get it here, but it does not give us any further result because we still get phenol. So HX phenol. But if it was suppose an alkyl alcohol, something like this, then what product do you expect in this case? In this case we would expect either an alkene or an alkyl halide. So you see the difference between aromatic and the alkyl halides. In aromatic halides, this HX have no effect and it just comes out as phenol. But in alkyl halides, you will either get an alkene or you will get an alkyl halide. Fine. But suppose I have some other thing here. Suppose CH3X. Now what? Now here this is an electrophile, and now we will get either ortho substituent or the para substituent. That means we will get two isomers, something like CH3 plus an equal amount of para substitution, OH CH3. We will get 50%, 50% because there is equal probability at ortho and para positions. But what about here we have some kind of a hydrogen bonding? Then in that case the ortho product will be preferred more over the para product, and in that case the ortho percentage will go up and the para percentage will come down. So here also all the factors which stabilize the ortho product or the para product are applied and the product will be determined in that case. So that means you have to be very careful in organic reactions. Any factor can come into play at any time. You have to be very careful. But generally you can identify the factor in a question, because that is why the question is asked. Otherwise why will the question be asked? You have to think like, why is this question asked? What is so special about this question that suppose hydrogen bonding is here, they are asking why the ortho product, the percentage is more than the para product. You see what is the structural difference between the ortho product and the para product, and then you would easily know it. Right? We will see many more electrophilic aromatic substitutions when we go to alcohols, phenols, and when we will study aldehydes and ketones. But for now, this much is enough. Now there is a class of reactions in which there is substitution reactions on the benzene ring. Let us see how that happens. There is a substitution reaction in the benzene ring. Okay, this was also a substitution reaction, but it was electrophilic aromatic substitution. But I am talking about the nucleophilic aromatic substitution which we have been doing in this chapter right from the beginning, the nucleophilic substitution. How can this nucleophilic substitution occur? That means if we take this as our reactant, this is some X, if we react it with some Z, then our product should be this kind of a molecule. And we know that this is not possible till now, but if we have some substituents on the benzene ring, that is, if we have some deactivating substituents on the benzene ring, suppose NO2. Now this NO2 is a highly deactivating substituent, that is, it reduces the reactivity of the benzene ring about some 10 times or some 1000 times. But other than reducing the reactivity, it also does one thing: it stabilizes the negative charge on the benzene ring. That is, if we write some mechanism, which I am going to write just now, in which there is a negative charge on the benzene ring and you need to stabilize the negative charge, what will you do? You will obviously add a deactivating group so that the negative extra charge which is present on the benzene ring, which is delocalized, is taken away from the benzene ring. Something like, if I have to suggest a mechanism for the above reaction, what I do is I will take Cl and I will attack Z in this manner. That is, Z minus was there, I will attack that Z minus over this carbon. Then what happens is the pi bond is broken and the electron density shifts over here. Now here you see that this is a kind of SN2 reaction, but in this case there cannot be inversion of configuration because this is a ring and it prevents the rotation, and hence the molecule cannot come from the back. This has to come on the same side, just as the thionyl chloride case where the Cl minus comes on the same side as the leaving group. Here also the Z attacks on the same side, because there it was for a different reason, here it is for it cannot come from the back side because of the presence of the ring and the electron cloud. Fine. Suppose I write this kind of mechanism for the above reaction. I can mention the reaction also. X has to be converted to Z. Now, if this reaction were to take place, I would write some mechanism like this. But now, this negative charge has to be stabilized. That is, negative charge, if I resonate it, if I resonate the negative charge Z, Cl, I have a double bond here, I have a double bond here. If I write one more resonance structure, I will have a double bond over here, I will have a double bond over here, negative charge this way, NO2, and here also NO2, and here also I will add NO2. So if I add this NO2, what advantage do I get? What advantage I get is, I get an extra resonance structure for this negative charge. That is, the negative charge when it goes into the NO2 group. So that gives me an extra structure, extra resonance structure, and that gives me a lot of extra stability. And hence, this mechanism can explain this type of reaction. That means this X can be in fact converted to Z, and this has experimentally been proven by doing several samples, testing, and by doing several experiments on it, that this is indeed the mechanism which takes place. Now let us complete the mechanism. That is, first the negative charge over here, which is stabilized by the heavily deactivating NO2 group. Next, what happens is, when we have this kind of structure, what happens is the hydrogen over here is in fact, and this Cl minus first of all thing leaves, giving a positive charge over here, and then this negative charge attacks this carbon, forming a double bond, and then a hydrogen is abstracted from here, and you get a proper benzene ring with the Z substituent. And this is called addition elimination reaction. That is, this is called bimolecular elimination reaction. Addition elimination reaction we are going to see next. There is one more mechanism which is proposed for this kind of nucleophilic substitutions, but that is in case if there is no NO2 group. That is, there is no deactivating group present in the ring, then how can the nucleophilic substitution take place? That is for that. Now this is called simply bimolecular substitution. There are two molecules and one is the leaving group, one is the attacking group. Fine. So this was a nice reaction where we have seen that even on benzene ring, nucleophilic aromatic substitution can take place. Now this substitution is given a special name, the nucleophilic aromatic substitution, and not just the nucleophilic substitution. Why? Because here the Z attacks only from the same side as that of the leaving group. It cannot attack from the back type. So it is SN2 aromatic. Fine. Now let us move on. What are the other possible reactions of these alkyl halides? We have seen just now a nucleophilic aromatic substitution. We are going to see one more mechanism for these type of substitutions, but in that case we won't have the deactivating NO2 group. Before that, some more reactions of this alkyl halides, aryl halides thing. Do you know Wood's reaction? In Wood's reaction, what happens is we take Rx and Rx, put them in sodium ether, and we will get RR. Quite the same type of reaction happens in case of aromatic halides also, and that is called Fittig reaction. What we do is we take aromatic halide, suppose X, and we take an alkyl halide, CH3CH2X. Now this we will use the same reagent, sodium ether, and what do you think is the product that we get? Now this is not any substitution reaction, this is just a kind of combination of one phenyl and one alkyl group. So this is the product that we get, that is these two X are removed or eliminated as X2 and we get this type of product. So this is called the Fittig reaction. And one more, we can see the formation of Grignard reagent also. We have seen the formation of Grignard reagent in case of alkyl halides, that is Rx plus Mg ether gives you RMgX. Same kind of reaction happens here also, but here the difference is it is not an aromatic halide, it is again an alkyl halide, but this carbon actually, if the halogen goes, the carbocation is in resonance with the benzene ring, kind of vinylic halide. Why? Because here if the halide goes, we have a carbocation, and which can be in, sorry, this is a vinylic halide, I was talking about allylic halide. This kind of halide, if the carbocation comes here, then this can be in resonance with the conjugation double bond, and similarly here it is delocalized in the benzene ring. So this also gives me Grignard reagent when I react it with Mg ether, and the product is something like C minus Mg2 plus and X minus and X minus. So this is another reaction of not exactly aromatic halide, but this kind of compound. Aromatic halide, a very important reaction is the Fittig reaction, and obviously the nucleophilic aromatic substitution. Now let us go to the other mechanism of nucleophilic substitutions. So that's it. These are the reactions of aromatic halides. We don't have any more reactions. So let us see nucleophilic aromatic reactions. But don't worry, we will see a lot of electrophilic aromatic substitutions when we go into further detail of organic chemistry, when we study phenols and aldehyde ketones, etc., etc. Now suppose you have a compound, you have an X, and you have a very strong base. For example, potassium amine. This is a very strong base, and you have this kind of aromatic compound. What type of reaction do you expect over here? What is the basis of the reaction and what is a possible mechanism? Here what we observe is we get a nucleophilic substituted product, something like this. We get an aniline. How do we get it? What is the possible mechanism? Here remember, we don't have any deactivating group which can be helpful in giving us this type of nucleophilic substituted product. So let us see, let me suggest a mechanism for this kind of reaction. Now the first step in this reaction is a very slow step which has to be stabilized as much as possible. So the first step in this kind of reactions is that this X minus goes off, and in fact no. The first step is the formation of a carbon ion, that is the strong base NH2 minus abstracts some hydrogen, either this hydrogen or para hydrogen, any hydrogen from here, and you get a negative charge over here. That is, the hydrogen goes off, leaving the negative charge over here. That means the pi bond is like this bond is like this, and this bond is like this. Fine. A very slow step because you are abstracting a hydrogen from a very stable aromatic system, and that carbon hydrogen bond is not that polar, so that that hydrogen can be acidic. But this is a proposed mechanism, and it has been experimentally proved that this is indeed the mechanism for the reaction. Okay, this reaction, in this case it is NH2 when we use KNH2. Now what happens? Now it is observed that when the carbon ion has come, this X leaves the system. That is, we get this kind of product, a positive charge and a negative charge on the carbon. Now actually these don't exist in this way. The actual reaction is when this leaves, this donates into this. So we represent it by this way and not by positive and negative charges. This is just for your reference that I have drawn the positive and the negative charges. So we get an intermediate which is a very important intermediate in organic chemistry. It is called benzyne intermediate. From benzene a triple bond comes, so it becomes benzyne. This intermediate is the intermediate which is formed in this reaction, where the first NH2 minus abstracts this hydrogen, and then the halogen leaves the system by creating a positive charge electron deficiency over here. So this donates its electron density into it. Now there are some special features about this benzyne intermediate. First of all, it is aromatic. Now you must be very much surprised about how can this intermediate be aromatic, because there is a triple bond over here, and for aromaticity you need only 3 pi bonds, not 4 pi bonds. The point is, this triple bond is not involved in the delocalization of pi electrons. How? Because if you consider the hybridization for these, this is sp hybridized, this is also sp hybridized, but the two p orbitals are actually perpendicular to each other. So only one p orbital can be in resonance with the benzene ring, because the perpendicular p orbital is, the electron density is perpendicular, and for resonance we know that the p orbitals or the electron density should be planar. That is, the p orbital must be parallel to each other in order to have resonance between them. So that means the third p orbital cannot involve in the resonance of the benzene ring, and hence the benzyne intermediate is aromatic, and that makes this intermediate quite stable, but not that much stable, because we know that there is a triple bond present over there, and that destabilizes the molecule very much, and hence it is an intermediate which immediately reacts to form what next? What is the next? Now this is a planar molecule, we know, almost a linear bond. What happens next is this NH2 minus attacks here. Now this NH2 minus can either attack over here or can attack over here, it doesn't matter. But when it attacks over here, it loses the hydrogen and we get NH2, and the aromaticity of the benzene ring is regained. So hence we see that starting from X, now we are left with only NH2 and the benzene ring, and it is experimentally observed by using isotopic effects that the NH2 can be present either on the position of X or a position ortho to X. And from this mechanism you can also say that if these two ortho positions are occupied, then this reaction cannot take place, because if these two reaction ortho positions are occupied, for example we have X, CH3, CH3, then in that case there is no hydrogen which is directly attached to this carbon, so that a negative charge can come over here and we can get this type of mechanism. So that is why we should have an empty ortho positions to this halide, so that this kind of reaction can take place. So this was a very nice mechanism, and we have seen a very important intermediate which occurs in organic chemistry, which is known as benzene. So another mechanism for nucleophilic aromatic substitution when the NO2 group is not present, but in the presence of a strong base. So that was the end of the lecture. I would just like to add a small thing. When we discuss the preparation of alkyl halides through alcohols, we have discussed the preparation of PCl5. Yes? So the question arises, why not PBr5 or PI5? We can use them, but there is a slight problem when we use the PBr5. The reaction, as we know it, is PBr5 gives you RBr. Now this PBr5 is actually very much unstable, so it readily dissociates into PBr3 and Br2, and that is why we don't get our product as RBr. So that is why we, in this case, we need to use PBr3, because then exactly that will give you a Br over here and the rest products will be formed. So with PCl5 and PBr3 will be used, right? So this is PBr3. Now this reaction is perfect, you will get RBr, no problem at all. What about PI5? Now already PBr5 is unstable, Br, and iodine is even more larger in size than Br, so definitely the PI5 will be more unstable than PBr5. So what should happen? We should use PI3. Okay, but the problem with iodine is PI3 is also unstable. So ultimately we go and use the PI2. So PI2 must be used to get the iodide, alkyl iodide. So our reaction becomes Ri. That is it. So this was a small point which I would like to add to the preparation of the alkyl halides from alcohols. And of course you should remember what leads the best results. Primary alcohols will definitely give lesser yield than the secondary and tertiary alcohols. Tertiary ones give the best yields. So that's it. This was the last part of the lecture. The end of the lecture has come. I hope you have liked the lecture, and please remember to learn the properties, physical, chemical, and the preparation methods. They will be definitely very much helpful, and go through the mechanism, the E1 and E2 mechanism which we had discussed, and the SN1 and SN2, and the comparison of E1 and E2, SN1 and SN2 is very, very important. You must remember the conditions when SN1 will happen, when SN2 will happen, and when the elimination reactions will take place. So that's it. Thank you.